Alrighty, so here's a homework problem out of Chapter 2, Section 2, and let me display the homework problem. And it says here that a function defined by two or more equations over a specified domain is called a blank function. And what are our answer choices? Odd, piecewise, even. Well, we could have a conversation about odd functions and even functions, but that wouldn't be the answer to this. The answer is piecewise. And final check, and very nice. So that we got the answer right. Now, what do we mean by piecewise function? Well, we mean a function that's defined by two or more equations over some specified domain. And you say, well, that was clever. You just read the question back. If you looked in your e-text, which is also available in Math Excel in Chapter 2, Section 2, you would find, a few words about piecewise functions, and they have the same definition that we just read in that question. And the idea behind the piecewise function is we have a function, that is, we have some output value that we can define with a rule based on some inputs, right? So that some output depends upon the value of some input, and then we process the input in a certain way to get the output. Notice the images they have there. They're saying that there is some situation where over a certain set of values, and these are minutes and costs, but you can see that for up to, it looks like 60 minutes, it's a horizontal line or a flat cost. But then after 60 minutes, in this example, you notice that the cost begins to go up. And so it is a function because there is some relationship between the inputs and the outputs. You'll notice that there's not any violation of the vertical line rule, so that we don't get confused about, well, what is the cost at a certain time. So it is a function, but we have two entirely different equations that describe it depending on where we are in the domain, or depending on where we are in the time. Now, the next question in that homework set is, let's go back to the homework set. We got that one right. Is this thing. The greatest integer function is defined by integer parenthesis x equals the greatest integer that is what? Greater than or equal to x, less than x, greater than x, less than or equal to x is the answer. And so there's our final check. We got that one right. Now, let's go back and look at that textbook a little bit. And a couple pages over, they mention step functions, a step function. And the one that they talk about here is this greatest integer function. Now, if you just take a careful look at their graph, and you can see that it appears that what we're going to do is we're going to round down a value to the integer value that is less than or equal to the value in question. Now let's, if I can, shift over to my pad for a minute, and I want to just do a couple of examples for this. One thing I want to, before I do that, let me point out to you that the symbology that they use here is int parentheses x, or some sort of double bracket looking thing there. And this particular function, the greatest integer function, is also referred to as a floor function. And I think you'll see that when we look at it on the pad. So let me crank up the pad here for a second. And let's go to this. Whoops, daisy, we were where we wanted to be. Shut this down over here. Now, notice that The idea, and here's my scratched out, sloppy looking graph, but the idea is that you want to round down to the nearest integer that's less than or equal to that value. So, for example, if the value in question is 9.9, and you want to have the greatest integer, then what value would you use? And it's got to be the nearest integer that's less than or equal to this particular value. So this would be 9. What about negative 7.8? It's got to be the nearest integer that's less than or equal to this, so it would be negative 8. What's the greatest integer function, or the floor, or the nearest integer that's less than or equal to pi? Well, it would be 3. And notice if you had a depiction here and we said, well, let's do one of these values that's kind of on my little graph. What if we had a value of 1/2? So what if I had 1/2? And I was curious to know what is the greatest integer that's closest to 1/2. And it's got to be less than, it's got to be the greatest integer. So it's got to be less than or equal to 1/2. So it's going to be what? It's going to be 0. So this would be 0. What about, oh, I don't know, 2.5? What if I had 2.5 here? Then if I'm at 2.5, here's 1, 2, I'm at 2.5. So I'm in this space here. So you'll notice that I'm somewhere between 2 and 3. And so what's the nearest integer that is less than or equal to 2.5? So the answer to this would be 2. Okay. So this thing is referred to as a floor function. And I hope you can see why they would call it a floor function. Now, our book used a kind of a double bracket looking kind of a symbology for this thing. Other textbooks use this bracket with a little bar at the bottom to kind of indicate that it's a floor. Now, believe it or not, in addition to the greatest integer function, there's the least integer function, and it's referred to as a ceiling function, and it works just in the opposite. Where in this case, we're going to round up to the nearest integer that's greater than or equal to that value. But the greatest integer rounds down to the nearest integer that's less than or equal. The least integer rounds to the nearest integer that's greater than or equal. So in this case, and we use these little brackets with a kind of a little bar at the top indicating that this is a ceiling. This is called a ceiling function. So in the case of a problem like 9.9, what is the nearest integer that's greater than or equal to 9.9? It's 10. Here we were looking for the one that was less than or equal to 9.9, so it was 9. Negative 7.8, think about it on the negative side, this would be negative 7 because negative 7 is greater than that. What about pi? It's going to be 4. And if you look, you can see that the depiction of the least integer function is going to have a similar looking graph, except notice that it's closed on the right-hand side, indicating the ceiling effect. These are closed on the left-hand side, indicating kind of the floor effect. So let's take my example here. What if I was at 1/2? What if I were at 1/2 here? And they said, what is the least integer that is closest to 1/2? The least integer that's closest to 1/2. I'm going to round up to the nearest integer that's greater than or equal to 1/2. So in this case, it's going to be 1. Here, it was 0. Let's go back to 2.5. What if I'm at 2.5? What if I'm at 2.5 and I want the least integer? Well, I'm going to say it's the nearest integer that's greater than or equal to 2.5. So in this case, it's going to be 3. So you can kind of see the way the graph looks here, that if I'm between 2 and 3, so I'm more than 2, but hadn't gotten to 3, so it rounds up to 3. And so this is referred to as a ceiling function. Now, you can say, well, how is this ever used? Well, think about postage rates, and I've checked this on the internet. This is not exact, but it's pretty close. So what kind of function is this? Now, what do you mean, what kind of function is this? Well, this is dollars, and this is I think these are units of weight here, ounces. So if this is international postage. So if you're sending something internationally by the U.S. snail mail, and it's from 0 up to and including 8 ounces, from 0 up to and including 8 ounces, it's $10.50. If it's from 8 ounces, it's more than 8, not 8, more than 8, up to 32 ounces, including 32 ounces. So it could be 9 ounces, 10 ounces, 12 ounces, 14 ounces, whatever. Then it's going to be $17.25. So you notice now in this case, what happens is you pay the higher amount if you're in this bracket. So this is an example of a ceiling function. You think, well, as long as it's between more than 8 but less than 32, I'm not going to pay more than $17.25. On the other hand, if it's more than 32 ounces, could be 32.1, but it's still going to be priced at this rate. If it's up to and including 48 ounces, it would be $26.25. So in this case, your postage rates behave this way. And so you could refer to the postage system as having a ceiling function. Now you can probably think of some other examples other than postage. Those of you that have used Uber, how does Uber price? Think about that for a minute. If you know how Uber prices, send me an email. Tell me how Uber prices. Is it a ceiling or a floor pricing structure? And tell me why you think what you think. Well, now, did we answer the question that we had a minute ago? I don't know if we did or not. Did we? Let's go back here. And let me get this to shut down for me. And let's see what we're doing. The greatest integer function defined by the integer that is less than or equal to x, where x is 2.2. The greatest integer that's less than or equal to 2.2 is what? It's 2, right? Good job. Now, what if let's change it a little bit. What if this had said the least integer function defined by the greatest integer that is greater than or equal to this thing? Well, it would have been 3 if we had a least integer function, greatest integer function and least integer function. Well, I hope this didn't confuse you too much. And so in light of that, I'm going to stop